Hello everyone, thanks for joining us today. We'll be talking about microservice architecture, one of the most popular and important architectural patterns nowadays. And the speaker today is Evgeny. I hope you remember him. And as always, I remind you that you can ask all your questions in the chat. We'll try to answer them. And please press likes if you like the video. And with it, I am passing the word to Evgeny.
Yep. Hello. Thank you for inviting me once again. And as Neil said, today I'll be discussing the topic of microservice architecture, which is really very popular nowadays. So, without any hesitation, let's begin. A little bit about me. Once again, my name is Evgeny Sokolchik. I'm a software engineer at EPAM Systems, and I'm working here for almost 2 years now. And I have been working on projects with monolithic application architecture, as well as microservice-like architecture. So let's firstly discuss about where it all began. So the monolithic applications. Let's discuss the benefits of monolithic applications. The first one is a simple development with all the code in one place. If you have a big application which has all the code, all the logics in one project, it's really kind of easy to navigate it because you may just locate your service that you need, locate another service which is connected to it, and check all the code relatively easy. It's easy to make changes because of the same reasons, and easy to test and deploy because you have only one application which has its own set of tests. And to deploy it, you just need to deploy one big artifact. So some people nowadays kind of hate monolithic applications, but it gets the job done. So now let's discuss some drawbacks. The first one is that it may be hard to understand all the logics and connections in a large code base. And well, it's really true for me, for me exceptionally, because I was working as my first project on a big monolith application, which was which had thousands of files, and it was intimidating to look at these for like the first months even. Okay, the next one. It's difficult to update to newer technologies. Well, it's a really big concern because if you have, for example, a newer version of your framework, it has no backwards compatibility, you just cannot update all the project in one step. You have to either stick with the technologies as long as possible or update your application step by step, really not too fast. Uh, another concern is that IDE may not be working well with large amounts of files. And it really is a big problem too, because when you have thousands of files, just loading the project will take minutes, and building it may even take like half an hour. So yeah, it's really a big problem. Also, load scaling is complicated because of resource requirements of every instance. So for example, if you have uh, any REST resource which is very popular among your users and they use it quite frequently, you cannot just uh, scale the usage of this resource alone. You have to deploy the new instance of your big and complicated application, which is not good. Also, every small change requires to retest all the application because of all the connections. And usually such applications have dozens of tests that may run up to an hour or maybe even more. So yeah, it's not very convenient. So let's introduce ourselves to microservice architecture. What is it? Simply put, microservice application is a collection of REST resources and logics behind them, as well as their own databases. This collection is built of standalone applications. For example, like on this picture, you can see that we have, for example, a catalog application, which has its own endpoint, logics for a catalog, and its own database. They communicate with each other using the combination of REST APIs or using asynchronous communication paths. And these things will be discussed later. And internal implementation of each service is hidden, which is really important because every service has a REST API, for example, and every service has logics, which can be tweaked whenever developer wants to do it. So if API stays the same, the logics behind the API can be redone in any way the team or the developer wants. So let's have a look at this little scheme that helps us to see the differences between the monolith and microservices. So the monolith is a big application with UI layer, business logic, data layer, and a very big database. While, as we can see, a microservice application is created from a lot of little microservices, which are like the monolith, but they are much, much smaller and they only do what they have to do. So let's discuss some benefits and drawbacks. The benefits is that services are small and simple to understand. Each service can be deployed and scaled independently. And if we return to the example I've used before, if you need to scale only one REST resource of your monolithic application, you have to deploy another instance. But if you need to increase the number of processing power of one of your REST endpoints for microservice application, you just have to deploy more instances of that exact service. All the errors are isolated. What does it mean? It means that if one service fails, then the others will work correctly. And if this service is failing, then we can just replace it by another one, just exactly the same one. Services can be independently written using different technologies, and that's kind of connects to the statement that internal implementation of each service is hidden, because we can create one service on a Python, for example, and another on a Java, depending on what do we need to create. And those services will be connected to each other by their REST APIs, for example, and by some other networking protocols. And it does not really, it's not really important how they are built internally. And development teams are creating code independently. That means that some team can be responsible for some microservices. For example, a Python development team uh, may work on Python microservices, while Java development team will work on Java microservices, which is really convenient, and they will only uh, be developing something that's that is in their jurisdiction, I might say. Let's discuss the drawbacks. The microservice architecture is hard to implement, especially splitting monolith into a collection of microservices. And yeah, it has to be a really big and hard and difficult architecture. It's not only an application which has some connections in it. It's a big amount of mini applications that have to speak to each other some way. So yeah, it's a concern. Uh, Development is much harder because of a split code base, because you just can't run a single application or a single ID, for example, for a single application and just find all the code you need. You have to open lots of projects uh, to find some logics if you are not sure where it is located. Also, deployment is complicated because of a large amount of elements. And yeah, when monolithic application can be deployed as a single artifact, here we have lots of artifacts that are kind of dependent on each other, and it makes this much harder. Now, let's talk about decomposition strategies. At first, what is it? Decomposition is a process of recreating your monolith as a set of microservices. So we decompose some services in monolith in a set of microservices. There are two main ways, by business capabilities and by subdomain. Let's discuss the first one. So the services must be cohesive and loosely coupled. What does it mean? Cohesive means that all they do, all their functions, all their methods must be created to work on a special problem. So, for example, if we take a login management service, all it is doing has to be connected to login management. And services have to be loosely coupled. What does this mean? It means that login management and catalog management should not talk to each other too much. Login management has to produce something that it can give to the catalog management, for example, service if it's needed, and they won't be communicating to resolve very simple tasks too much. Um, then, every service must be defined corresponding to business capability or should generate any value or business value. So basically, it's really simple. It's a really simple strategy. For example, login management service or management service must generate value by creating uh, a login actions for the user. Catalog management must create some actions, must implement some actions to manage the catalog authentication and so on. So they all have some business value for the customer. And development teams become cross-functional, autonomous, and organized around delivering business value rather than technical features. It's very good for business and quite convenient too. And by subdomain, another strategy. Services must be cohesive and loosely coupled, once again. And here comes the domain-driven design. The domain-driven design approach is a way of building complex applications based on the development of an object-oriented domain model. What does it mean? It's quite complex to understand, maybe, but it's kind of similar to creating our object-oriented applications using the object-oriented language like Java. So we must think about our problem, our business problem, for example, and create an abstract solutions for this. For example, we have some clients. We have to create some login management service. So what's the main model it will be acting with? It will be acting with the user. So here we have a user domain service. The scope of a domain model is called a bounded context. So if we have a user domain model, for example, then everything that is connected with this domain model can be called a bounded context, and a bounded context is usually can be converted to the microservice. And here, for example, we have an e-commerce domain, and it has a user management subdomain, which is just a part of an e-commerce domain, catalog subdomain, and so on. So each domain includes corresponding subdomains. And identifying subdomains is the same process as identifying business capabilities. So it's just a little bit different approach. For example, here we can see that we create a login management service, which is a business value. We manage logins. And here we build kind of the same service, but it is created around some domain model or user domain model. So these two approaches do the same, but in a little bit different way. So when we thought about decomposition, how can we implement this decomposition? We can do it by introducing the Strangler pattern. It incrementally transforms an application by replacing a particular functionality with a new service. And as soon as the new service is ready, the old component is strangled and the new service is put into use, while the old component is decommissioned. So what does it mean? What does it mean? Basically, that we recreate our monolithic applications into a set of microservices step by step. We recreate some functions from monolithic application in service A, then some more in service B and C, and so on, while our monolithic applications is still in use. And someday we'll come to the state where all our monolithic application has become a set of services. And here, to understand a little bit more about decomposition patterns, I've got some statistics. You can see here that both those approaches are used to decompose, and they sometimes even used combined, and even in the most they mostly used combined. So they just you don't have to choose any one of those. You just have to uh, think about your problem and solve it with whatever instrument you find useful. So do we maybe have any questions? Anyone? After the chat?
Yeah, I'm looking. I don't see any questions for now. I think I will give like 20 seconds for our listeners to ask what they are interested in, and we will have a small commercial pause. I just remind you guys that we have a totally free online Java school that starts with very basics of Java and goes up to modern frameworks like Spring and even Cloud, CI/CD, and other advanced techniques. So if you're interested, just go to mjc.school and enroll today for free. Okay, and uh, I'm taking a look again, and we don't have any questions for now. I think we can proceed.
Okay, then I'll proceed with the presentation. So let's discuss a little bit about monolith decomposition challenges. The first challenge is a network latency. That is a constant concern in a distributed system, because we are recreating our monolith, a tightly coupled application, into a set of network connected microservices. We have to think about this concern because it can slow down the work of our application as a result. So it's really important. Next one is maintaining data consistency across services. Each service would have its own database, so maintaining data consistency across those services would be really difficult. Next thing is guard classes. It's an object that control too many other objects in the system, grown beyond logic to become the class that does everything. And while it's a major concern in every type of architecture, even in monolithic architecture, uh, sometimes engineers can be engineers and say things like, don't touch what's working good enough. uh, and it will be living well in a monolithic application. When we try to decompose our monolithic application into microservices, we have to get rid of those guard classes because microservice architecture just won't work with those. So later in this presentation, we'll discuss on how to reduce network latency and reduce the concern of maintaining data consistency across the services. We won't discuss the get classes because get classes is an anti-pattern in every architecture. So let's discuss microservices communication patterns. There are two really main communication patterns, so synchronous and asynchronous communication, but asynchronous can be divided into two. So we'll look at them like three patterns. So synchronous communication is using protocols like HTTP, HTTPS, or gRPC, and it returns synchronous response. So client must wait for response before continuing with any other actions. So here we can see on the image to the right that every service communicates to the other service using an HTTP synchronous calls. Asynchronous one-to-one communication uses protocols like AMQP or Advanced Message Queuing Protocol for message queues. So client sends a request, but it doesn't wait for a response from the service. So here we can see that every service is connected with the other one using a message queue. And asynchronous publish-subscribe model, uh, it's also called sometimes one-to-many or many-to-many model. Unlike one-to-one, pops up it's a more convenient name for it, pops up, uses message topics which services subscribe to. So those topics can receive and send messages to many services at once. Now let's have a deeper look to each one of those patterns. Synchronous communication. Client calls service A, which then calls service B, and so on. And every call in this chain is a blocking call. So every service will wait until response comes before it will be able to continue processing other requests. While it's not a very big time, but when we're trying to reduce the network latency in our system, it's really important to reduce the waiting time for every service. So obviously, it's not a very efficient way of establishing communications between our microservices. And sometimes it's even called an anti-pattern for modern applications. At least I've seen in Microsoft guidelines, they're calling it an anti-pattern. And here comes an asynchronous one-to-one communication, which helps us to mitigate a little bit of that network latency. Client calls service A using an HTTP or HTTPS protocol. For example, client is our user through the site. And then the service A is setting an AMQP message to the queue, which service B is listening to, and so on. So every service is listening to the message queue and acts on new message arrival. That means that service A can accept a request from another client immediately without being blocked for some time. It helps to create a more efficient systems, and also it is one step on a long way to creating an event-driven architecture. Then asynchronous publish-subscribe model. It's probably the most popular approach nowadays, and it's very similar to one-to-one models, except it's using topics instead of queues. When using topics, as I already said, they can be multiple producers or services that produce messages for other services, which are stored in those topics, and consumers of those messages that are taking the messages out of the topic and uh, do some work on it. And the most popular tools for async communications are RabbitMQ and Apache Kafka. And they both have functionality of queues and topics, but RabbitMQ is mostly popular in one-to-one model, while Apache Kafka is really popular for publish-subscribe. So let's discuss the next concern, the data consistency. To address this concern, we can use the microservices distributed transactions. Because every service in microservice architecture has its own state of data in its own database, the problem of data consistency, as I had already said, must be addressed. So transactions are used for data to stay consistent in a database for any application. For example, in our Monolith, we always use transactions for our data to stay consistent. And distributed transactions are used in microservice applications as they are distributed systems. So if something goes wrong with any service, all the services must react. For example, uh, an order service creates an order, payment service validates payments for some shopping application. Then something bad happens in inventory service. So what should we do? How other services must react? Let's discuss it here. Saga pattern gives the answer to this question. It offers to create a set of transactions that update microservice sequentially, for example, creating an order for order service and validating payment for payment service, and publish those events to, for example, a message queue to trigger the next transaction for the next service. So every service will do the transactions step by step, one by one. In case of failure on one of those steps, rollback transactions are triggered, which basically do reverse operations and publish rollback events to previous microservices. So if in a monolithic application we can use a transaction and roll back a transaction, here we have to have another transaction which will be called a rollback transaction. So the Saga pattern uses a sequence of local service transactions for transaction management. Rollback transactions is a set of compensating transactions that roll back the changes on previous services. So, for example, if something goes wrong on an inventory service with updating the inventory, then rollback inventory transaction will be used. Canceling payment for payment service will be used. Canceling order for order service will be used too. And all our data will remain consistent in all the three services that were affected. Also, there are a choreography and orchestration implementations of a saga pattern. What is choreography? It means that we are using a pub-sub model. So when I already said, when some service completes a transaction, then it publishes a message to a message queue, and then the other service is doing some transactions on its data. So every service just tells the other service, the next service in the chain, what to do. And there is an orchestration model or with a centralized controller, which operates on those services and tells them when it's time to use their transactions to change their data, both transactions for adding data and rollback transactions as well. So let's discuss a little bit about orchestration and choreography for microservices, not only the saga pattern. And as you may already have guessed, for microservices architecture, orchestration pattern means that there is one orchestrator or an app that controls all the other services. While using a choreography pattern, we are letting those services to communicate to each other using an event broker like Kafka or RabbitMQ. So orchestration use orchestrator or controller that communicates with each service. The invocation of each service take longer because requests should be passed to this orchestrator, and this orchestrator will call the service you need. We'll have a tight coupling of microservices in that way and a single point of failure. Because if our orchestrator will fail and stop working, then all of our applications, all our little microservices won't be able to connect to each other. And choreography gives us loose server coupling on the other side, faster and more agile development because every service is less dependent on others, for example, on an orchestrator. And it gives us a more consistent and efficient applications that won't fail just because orchestrator has failed. So maybe we have any questions, Danila? Can you check the chat?
Yes, actually, we have several of them. The first question, yes, let me open it. Why to use messages instead of communication over REST?
Well, as I already said, messages help you to create communications between microservices asynchronously, which means that the service that calls another service will just publish some message in a queue, and it won't wait until the response comes from the next service. It can proceed with some additional operations, and it kind of reduces the latency of the whole system.
Yeah, also, I'd like to add that it decouples the systems. Your service that sends a request doesn't have to know anything about the consumer of the message, and you can change them however you want. You can remove completely the consumer and just send messages to the queue, so nothing will break. And also, queues allow you to mitigate the spikes of traffic. So, for example, you have 1,000 requests per minute, and the next minute you have 10,000 requests. If you are just using the REST, your servers may crash because they cannot handle such load. And with the queue, for example, Kafka, the messages will be just stored in the queue durably. They will not get lost. And when the traffic slows down, the consumer will process the events. So actually, there are a lot of advantages, but not all the communication can be made asynchronously. So sometimes you have to use REST, and you don't have any choice.
Yep, that's correct.
Uh, okay. Uh, there are some more questions, but I don't quite get them. I'm sorry, guys. Maybe we will try to answer them later. And for now, I think we can proceed.
Okay, thank you, Danila. So let's proceed with the presentation. And now let's discuss about creating microservices in Java. There are lots of tools to create your microservice applications, but here I have written the most popular of them, I think. So the first one is a Spring Cloud, which helps you to create a service structure. What that means, that's using the Spring Boot framework, we can create microservices, but Spring Cloud framework helps us in connecting those services to each other. For example, it has some useful integrations with some other popular microservices and cloud instruments, and we'll discuss it a little bit later on the next slide. Next is Eureka. It's a service discovery application, which is really important. Uh, really important part of every microservice application, and that's why we will discuss it a little bit later too. Apache Kafka and RabbitMQ, those are message brokers. We have discussed them earlier. The Docker, the thing that I was talking about on my previous slide talk, it helps with development, and of course, it helps with deployment of services using the containerization. Then Kubernetes or OpenShift or some other container orchestrators can be used to simplify your work with thousands of containers. Next is Zulu Server or an API gateway application. We'll talk about this one too. And the next is Prometheus and Grafana, an application monitoring stack. Prometheus is an instrument that helps you collecting data about the work of your microservices to monitor them, and Grafana is a tool that helps you to visualize all the data that you get from Prometheus. So let's discuss Spring Cloud. So yeah, Spring Framework is a model, it's a Spring Framework model that has a lot of useful functionality to create microservice apps. So Spring Boot is used to develop a standalone microservice, while Spring Cloud is used to configure the communication between those services or to create our whole infrastructure. Spring Cloud has integration with Eureka Server via Spring Cloud Service Discovery. And for example, when we're creating communication between our microservices, we can use Spring Cloud Kafka integration. Of course, we can use a Kafka API in our Java classes and create communication between our microservices without Spring Cloud Kafka, but Spring Cloud Kafka makes it really easy, and you can connect two microservices by using just two annotations and a little bit of configuring. You don't have to write too much code with it. So service discovery or Eureka. It's an app that contains addresses of all the services in the network. So if we have a big microservice application with a lot of services, we don't need to hard code address for every service into the other service that communicates with them. We just can call a Eureka server, which contains the names of services, and it will look up for its IP and port using Eureka. For example, if we register the service A and service B on the image in Eureka, then service A, when it wants to communicate with service B, can present the service B application name, and it will obtain the network location or IP and port of it from the Eureka. and then it will use all the information to communicate with the service B, which means that services do not need to know anything about each other, only their name maybe, and that loses the coupling of the services as well. And last but not least, let's discuss what is an API gateway really briefly on an example of Zool server. It's the one point of access to all the microservice infrastructure. Often applications that are based in cloud use their own private networks, which is used to communicate with for microservices to communicate with each other, and we can access all this internal network using only one point of only one point in an application, which is an API gateway. Why can we use it? For load balancing, for example, if we need to, if our application needs to scale up some of its REST resources, then our gateway can use all its knowledge about our system and send a request to the other instances of the service with the same REST endpoint. It can route requests dynamically, which also helps with load balancing or with any failures of other microservices. It helps with also requests filtering. For example, if you want to filter all the requests that are coming to our application, we can do it all in our API gateway and don't have to do it multiple times in multiple places. And also, Zool Server works great with Eureka because it can obtain all the addresses of microservices in our system through the Eureka, and it doesn't have to know anything about their IPs and ports before accessing the Eureka, really. So that's all I wanted to discuss about instrument stack. Maybe last time we have any questions, Daniela?
Yeah, actually, we have three questions right now.
That's a lot.
The first is why do you need Eureka these days if all its capabilities are in Kubernetes already?
You can use, well, if you are not using containers, for example, you will need an Eureka to do the same things that Kubernetes can do. Yeah, actually.
Yeah, I would say that Kubernetes solves a lot of issues, but not all projects use Kubernetes. And sometimes you need to change something in the behavior of the service that you're trying to use. So if you solely rely on the Kubernetes, there may be no extension points that you need. And if you deploy your own solution, for example, Zool, well, it's not your solution, but you deploy it and you can extend it however you want. And well, yeah, it's easier to change in some cases. But yeah, I agree that in most cases, probably you don't need to deploy these services yourself. The next question is, can we say that API gateway is just a load balancer?
Well, it's not only a load balancer. I've discussed some more features about it. It can filter requests, for example, and so on. So now load balancing is only one of its features.
Yeah, and usually API gateway is used for routing. So, for example, you can have two microservices, route A and route B, and all the clients send the request to the API gateway, and it itself decides to which service A or B should it send the request, depending on the URL or headers or the cookies. So it's not only a load balancer. Yeah, I agree.
Well, maybe
And
even
yeah,
dependent on an availability of those services. If one is down, then the other is up, and it will choose the other one.
well, I think it's a part of a job of a load balancer too. So it should ignore the dead microservices. But yeah. Okay, the next question is what is the typical file structure for microservices projects look like? Are services separated or they can share one root POM file for main project for all microservices?
Well, usually it's completely different projects that have their own POM files. And the structure is quite the same as in the Monolith, but it's just smaller.
Yeah, usually I would say it's like controllers, services, or business logic, and data access layer, and maybe some other folders. But yeah, uh, they're pretty same as for monolithic. And what about separating services or using a single POM file?
Sorry, can you repeat, please?
Yeah, are services separated or can share one root POM file for all microservices?
Well, sometimes they can share, of course, they can share one configuration file, but um, they will share some information from that configuration file and will need some of their own configurations in their own configuration files as well.
Yeah, if you need to reuse some configuration or some code between different microservices, you don't have to put all of them in one repository. There is a common pattern when you extract some shared library, they're usually called like that. So like shared login and the name of your project, and then you import that library to all of your microservices, and you don't actually need to put all the microservices together.
Yeah, sounds about right.
Okay, we have few more questions. Netflix
Nice.
themselves already abandoned their old stack, including Erica. Does it make sense to invest in Erica knowing that? I think we partially covered it. If you just need a simple load balancing or well, simple features, then I think no. For example, if you are using AWS, so there is an AWS application load balancer that can do everything you need. But if you have some more advanced requirements, well, then you definitely should. I personally worked on the project where we extended Spring Cloud Gateway, and we couldn't use any existing solution, and Spring Cloud Gateway helped us a lot, and it saved us, I don't know, maybe a year of development by providing some already existing code. I hope it answers your question. Okay, another comment is they say that Java apps are too fat for microservices. JVM, Spring, Servlet Container, they eat resources. What do you think about future of Java as a microservice platform? Oh, great question.
Well, yeah, it's an interesting one. Well, Java is not considered really a cloud native language nowadays because there are others like, for example, Go, which is developed to create microservices from ground up. So maybe it's not as efficient to build those services in Java, but Java is still a very popular language. It's kind of easy to use to create and develop some e-commerce or other enterprise applications. So I think it will have its place in the future of a cloud and microservices. Maybe not maybe not forever, but for a long time for sure.
Yeah, well, there are companies, huge companies that are using Java. They will not switch to any other programming language. And about the usage of resources, I think that Java nowadays is not as fat as it used to be, and there is a lot of job done to optimize it for cloud. So there are like native images that are compiled beforehand, and they can start within a milliseconds, and they run extremely fast. So I think that the Java in the course of 5 or 10 years, it may change a lot, but I don't think that it will die. Okay, we are having more and more comments here. Besides Spring, there is Quarkus, Helidon, Tor, etc. How to choose a framework for a new JVM microservice?
Well, I think, it's not about today's presentation, but I think you have to deep dive into all the features of those frameworks and just find the one that suits your specific task really well.
Yeah, I wouldn't use some frameworks that are not mature, so which are were not released yet, or that have less than, I don't know, a few hundred stars on the GitHub. And probably if you already have several applications using Spring, then you should stick to the Spring, because you probably have some shared libraries for logging, tracing, monitoring, etc. And you can do a lot of job by importing, by writing 10 lines of code in your new microservice. And if you switch to Quarkus, which is great, but you will have to rewrite all this logic using new framework, and it takes a lot of time. And I think the last question would be, do you find native compilation with GraalVM valuable for the microservice use case?
Danila? I can't comment on that.
Yeah, I haven't really used GraalVM, but from what I know, it's a great solution that doesn't match all the cases, and maybe they fix some problems that they had when I read about it. But I think that native compilation is one of the paths that Java can take in the next years. If it reduces the startup time, maybe the warm-up time, and maybe it can do something with resource requirements like memory and CPU, it can be a huge win for Java. But for now, if you're just starting new projects, I would recommend to stick to usual hotspot VM, and I don't know, Amazon Careta is a GVM, or any other, it doesn't really matter. And yeah, for now, I would not use GraalVM. And yeah, that's all questions that I see for now. So I think we'll be wrapping up. Thanks, guys, for joining us today. Thanks for a lot of questions. It was really interesting
Thank you
answering all of them. Yeah. And see you next week. Thank you and bye.
See you. Bye.